All right, and is the audio back? Good. All right, so we are back. So we, in the last video, we just went over kind of our first example of how to calculate, really, we did range, yes, but really variance and standard deviation. That's really the important thing we were looking at. So I want to start this video with, let's go over another one, just kind of work through it again. And I also want to both clarify and talk about one of the things I was mentioning on the end of that last video, kind of the difference in these calculations when it's a sample versus a population. On that last example, I thought it was a population, and so the calculations we got were literally, I guess it would be like lower than they would have been for a sample. So I want to kind of flesh that out, like why is that? How does that work? So let's start there. Let me go ahead. Yeah, let me go ahead and do this and get an example up. Window 4 is actually 14. And let me size this up for y'all. So we're just gonna have second. It's the one we did. We did that one. All right, good. So we want to calculate we want to calculate range. So this question, if you take a look at what it's asking for, it's asked for the same thing. Find the range, variance, and standard deviation. The range is easy enough, right? Let's figure out how I'm going to use this space. But yeah, the range, like we've talked about, is just highest minus lowest, right? And let's see, highest there. Highest looks like a 71. Lowest. Just the 49. I believe it's the 49. Yeah, looks like the lowest is the 49. Subtract those. My range here is 22. By the way, let's talk about the context of the problem. Sorry. So this is a sample of 12 drivers that shows the time they spent in minutes stopped in rush hour traffic on a specific snowy day last winter. Find the range, variance, and standard deviation for the data. So this is one particular day, one particular snowy day. And notice they go out of the way to say this is a sample of 12 drivers. So like I said, as we go through this calculation, we're going to do this. I'll show you there's small adjustments we make in the calculation. And when I say that, I mean really not at all to the procedure, but there's small adjustments we make when we're calculating sample versus a population. Specifically the variance of the standard deviation. So I actually wish if I could move this. Well, let me talk about all the words and then we'll move it over. So So this data, maybe they're using this to try to prove or try to get some idea of the variance and standard deviation of people's wait times, right? On snow days. So this is one particular day, and it may not represent all snow days well, but maybe it does. Maybe they chose this because it was sort of, from what they can tell from the population. So again, notice that this is a sample of 12 from one day. What they're likely doing is comparing this data, not just likely, what they're doing is comparing this data to a large population, right? All different, we're trying to make some claim about an average snowy day. So must be some, there must be some data or some, what do you call it, information about all snowy days or most snowy days in this particular area, in this particular town. And we pull a sample of 12 from one snowy day so we can get an idea of, again, what's our, you'll see we're going to calculate the mean. So we'll already, by doing this, you guys saw last time that to calculate variance and standard deviation, you need a mean anyways. So we're going to calculate a mean, and that'll give us an idea of the middle. Again, we'll talk about, we know that mean is not always a good middle, but in order to have a reliable calculation, like I was talking about last time, we use the mean for variance and standard deviation. But we'll have an idea of the middle. And then with variance and standard deviation, once we can calculate that, we'll have an idea of, again, spread. So variance and standard deviation are about spread. Ultimately, standard deviation is what we're looking for. What is the average spread, or what is the expected spread away from that middle, which we'll use the mean for the middle. So good. So that's kind of what they're trying to do with this. Now, let me make some room here so that, yeah, actually play with this. All right. So we want to go through and calculate variance and the standard deviation. A bit like we did last time. The first thing you're going to need to do here, so we need to build a column that just lists all this data. You can list it in any order that you want. I'm going to list it from lowest to highest because it gives me, I think like I was talking about last time, for me, at least visually, it actually helps me sort through the data and the calculations and sort of their relative amounts and position to each other to have it listed from lowest to highest. Don't have to, but I'll kind of list it that way. So this is our data. And let's see. So lowest to highest, that means the first one is a 49. Second one is what? 51. I know it's kind of, actually, let me have you guys do this really quick first. I know it's a small thing, but again, my point in these couple of examples is I do really want you to learn how to kind of build out this table and therefore calculate variance and standard deviation by hand. And you'll see as we get to later in the course, I mean, you guys have a calculator, you're going to be able to use that. But basically going to, we're getting close to this first test. I think the big thing out of this is I want you to really understand why and where that variance and standard deviation comes from. So I want you to do it by hand at least once. So that'll be kind of this test. When you get to this test, and it won't be actually many problems, probably just one, but I do want you to calculate this thing by hand. So let's give you practice sort of building this table and getting this calculation going. So the first thing I'd like you to do is I guess you don't have to list the data from least to greatest, but if you want to, so just go ahead and list the data from least to greatest or however you want to list it, but get a column going with all the data first. And then, like we did on the last example, we'll kind of move to the next column we need. So go ahead and pause on your side. I'll pause on my side. Good. So I'm going least to greatest. So 49, 51. It looks like we have a 52. Looks like we have 353s. Then what comes next? Sorry. It's like 56 is next. mistaken. And here I'll kind of continue it down here. Let's see, it looks like we have 258s. See, so I can check myself. So we have 12 total, right? 58, D8. Keep going. We have a 60 next. Like we have a 61. Oh man, this do not be so long. Let me try to erase some of this and just make it smaller. At least one more down there. Let me count this up. That 1, 2, 3, 4, 7, 9, 10, 11, 71 is going to be the 12th. So that's perfect. This does get everything. Where can I get some? $29. D1. Extra out of this 52, 53s. Six. D8, there we go. There's my extra line. Second 58. And 60. 61. $71. Good. So that is all my data. And so the first thing we need to do is calculate a mean of the data. All right, because again, so remember our whole process. Variance and standard deviation is about literally deviation. How far is the data away from a middle? But we need a middle. And because we can calculate it the same way every time, we're going to use the mean as our middle. So your first job is to take all this data and calculate the mean. And you don't have to have that data, that result any particular place, but I basically am going to put my mean down here because you'll see as we go, we basically are be putting all our means down here. So I'm going to start another column down here, and this column is going to be my mean. Just want to label it. I don't know. Hopefully you guys can see that. That is my mean. So that's the first thing I need you guys to do is calculate the mean. And really quick, I want to talk about, I think, either misstated or just kind of I'm not really mixed up. But when I was talking about sample at the end of that last video, when I was talking about samples versus populations, I was talking about sort of that n-1 that you divide by one less. That dividing by one less though is only for variance and standard deviation. So the mean of a sample is still the same, like we learned, you know, in the previous videos for the week before. The mean of a sample is always add them all up and divide by how many there are. So mean is always the same. So we'll start there and then talk about when we get to variance and standard deviation, we'll talk about the difference because this is a sample versus a population. But the first thing is go ahead and calculate your mean. And go ahead and pause for a second on your side and I'll do the same on my side. Let's go ahead and calculate. All right. So what I'm seeing here, when you add all these up, you should have got 675. You divide that by 12, you should have got 56.25. So my mean here is 56.25. We're saying 56.25 is roughly the middle of our data. And notice that at least for the spread of data you see, especially since I haven't written least to greatest, that kind of makes sense. It looks like it only looks believable, but it looks like it's about the middle. We do have a bunch of data from basically 49, early 49s and 50s, right up to about 56, and then jumps to 58. And we have a couple 60s, and then this 71 that's really far away from all the data. So honestly, that 71 is probably pulling this mean. Last week we talked about the mean, or a couple weeks ago, or whenever it was, but we talked about how the mean is really sensitive to really high or really low numbers compared to the rest of the data. So the 71 is honestly probably pulling this average up away from the 53. If you think about it, both in terms of mode, median, etc., the middle of this data should be close, should be more like 53. It should be closer to 53 at least. In fact, if you did the median of this data, what, 1, 2, 3, 4, 5, 6, it would be halfway between 53 and 56, which is 54.5. So anyways, so the 71 affects that mean a little, but still 56.25 is a good middle of the data. So that's our mean. Now, what we're trying to calculate is deviation. How far is this? And what we're trying to get a concept of is how far is our data away from the middle? So we now know our middle. So our next column is deviation. And to make it so we don't take a ton of space, I'm just going to put dev there. But what I want to do is I want to figure out what's the difference, the deviation, the distance. What's the distance between this 49 and 56.25, and then the 51 and the 56.25? How far are each of these bits of data away from now our middle, what we're calling our middle, 56.25? So that's your next job, like we did last time, is now let's do some subtraction and find distance. So how far is 49 away from 56.25? And when you do that, by the way, I mean, as long as you're consistent with the way that you do the subtraction, doesn't matter. But as a good rule of thumb, think about how the 49 is below the 56.25, right? So my distance there, or my deviation, really not quite distance, but anyways, my deviation should be negative because I'm less than the 56.25, right? So when you're doing the subtraction, you always want to start with the number and subtract your mean. So the value minus the mean, just to get your positives and negatives to jive with the way that they do this. So if your number is below the mean, it should be negative. So you should be doing 49 minus 56.25. So you make sure you get a negative. So again, remember my deviations are going to be both positive and negative. But anyways, so that is your next job. Fill out this deviation column. So the distance away from 56.25. So go ahead and pause and do that. And I'll pause on my side. All right. Oh, so, let's see. If I look at during, let's go back to, it's the same as it did before. Good. Okay. All right. So deviation. So 49 to 56.25. That's going to be negative 7.25. At 51 to 56.25, that deviation is negative 5.25. 52 to there is going to be negative 4.25. The 53s are all going to be negative 3.25. The 56 will just be a negative 0.25 or 0.25, however you like to write that. And everything above everything below this is gonna end up being positive numbers. So 58 minus 56.25, you should have got 1.75 there. So we'll have two of those. Continue this down. 1.75. 60 minus 56.25 should have been 3.75. 61 minus that is 4.75. And then 71 minus that is what? 14.75. And that would have been all your deviations. And now we talked about on the last video that, so I mean, this is the true, like, this is the distance away from the middle, right? But these negatives cause us issues if we're gonna then, like, again, I think the most logical idea from here would be, oh, let's just take an average of, let's take the mean of all these. And the problem with that is that that tends to go to zero. In fact, it should go exactly to zero. Or at least it should tend close to zero. 10 close to zero a lot faster and a lot farther away from the actual spread value that you should have. So you can't just use the deviations. And it's because of these negative numbers. So we need to get rid of them. We talked about on the last video, what you should do is should take the absolute value, but that is actually, as far as getting a calculator or computer to do this, it's actually hard to program and just doesn't have a reliable, what do you call it, formula for it, right? So instead of that, what they decided to do, they decided to square these numbers. So we're going to have the deviation squared purely because a negative times a negative is a positive. So it's one of my ways mathematically of sort of getting rid of negatives when I need to. So this next column is going to be the deviation squared. So you're going to take all these numbers and square them, write them down. And then remember that the mean, well, okay, actually, but let's do that first. And then let's talk about mean of the squared deviation. So this is the deviation squared, or you can call it squared deviation. So that's your next job, is go ahead and, like we did on the last one, go ahead and square all these numbers. Do that all the way down, and then let's see what we get. So go ahead and pause on your side, I'll pause on my side. All right. Okay. We get a little handy dandy calculator. They're not horrible to square by hand, but they take a little time, so this will make it much easier. So 7.25 squared. Oh, 25, and let's square that puppy. All right, so this first one should have given you 56.5625. One note too, now that I think about it as I'm writing this, don't round these. And the reason for that, well, one of the nice things about, at least when you're squaring this, when you're squaring these numbers, the decimals may be long, but they are exact, right? They terminate. So if we're looking for an exact answer, or at least, our best approximate answer by the end of all this, we want everything in the process to be as exact as possible. So if you think about it in terms of like manufacturing, right? So if you have some manufacturing process, anywhere in that process, if you have some, what do you call it? Yeah, you're making some cans that you're going to put something in, or I don't know, but you have something rolling down a, what do you call it? I can't think of words right now. Second. A conveyor belt and like a, factory. And there's several things being done, many things may be being done to whatever object you're making. If you introduce error somewhere in that process, right? How big does that error become by the time you get to the end of that conveyor belt? It becomes pretty darn large, right? So if you want things to be accurate, even like in a manufacturing process, you want to control that error, have as little as error possible, at station A and then station B and then station C, really all the way down the line as much as possible. So you have as little of error at the end as possible. So you want to think about math calculations the same way. If you introduce error somewhere in here before we get to the end, then the end is, at the end, we're going to get something that's off from the best kind of either exact value or at least approximate value that we can get. We're going to get something that's a good bit off by the end if we introduce error sort of in the middle of our process. And so we want to control that as much as possible. So the problem with rounding is if you go and round this, you're chopping off some of the value there. So you're introducing error there. And so that error is going to get magnified as you go by a good bit. So when you're squaring this, especially since we're getting exact decimals with which terminate, never round those. You want all of that. You want all that decimal because that's an exact value. So right now going through this process, we wrote everything down. We took a mean. The mean was an exact decimal. So 0% error, 0% error. We're getting exact values here. We want to keep it at 0% error so that the only place that we really get any error or approximation is at the end when we have to round, right? And so then we're going to get a really tight, really close value to whatever theoretically is the real value for this. So hopefully that kind of makes sense. So again, especially if you're getting decimals like this, that which you should be on all of this. Maybe they're long, but they're exact because they end. Please do not ever round them. You're just going to introduce a bunch of error to your problem. Anyways, so let's keep going. All right, so 5.25 squared, or negative 5.25 squared, sorry. That is 27.5625. And then negative 4.25. 18.0625. And then our 3.25s are negative 3.25 squared. Each of those is 10.5625. Negative 0.25 squared. It's going to be 0.0625. All right, so it's looking like this column is long enough to kind of contain all of these. So then we can go with the 1.75 squared. So each of those should be 3.0625. And 3.75 squared is 14.0625. 4.75 squared is 22.5625. And 14.75 squared. We'll talk about actually when I think it's sections 3.3 and 3.4. We talk about things called outliers. We are outlier way outside of everything else. That is 217.5625. That adds a lot to this. But that is all my squared deviations. So then remember that your variance is your mean of your squared deviations. So on the last example, what we did is then we just took all these and we divided by how many there are. When it's a population variance, that's what you do. You divide by how many there are. However, so this is where I wanted to make that, or just go back to that clarification I was talking about last time. When it's a sample and we do variances, or basically our variance, you want to divide not by the full amount, but by one less than that, by n minus one. So like there's 12 numbers here, 12 bits of data. When we do the mean of our squared deviations, so the mean of the squared deviations is the variance, we're going to divide by 11 and not 12 because it's a sample. So the reason is because it's a sample. And to give you an idea of kind of why they end up doing this, because I think it's not only it's good instinct, but it's a good question. Why would they suddenly do it differently for a sample? Like, that's not what a mean is, right? You're supposed to divide by how many there are. So think about the idea of again, a sample. So we're picking 12 drivers. So they didn't even pick everybody on that snowy day, right? They just sampled just 12 drivers out of probably a bunch of them. And again, that's one snowy day out of a bunch of them with a lot more drivers, right? So this 12 that we're picking is, if you think about it, kind of small compared to the whole population of snowy drivers and all their snowy drivers. Yeah, we'll go with that. Snowy drivers and all their wait times. So what happens is when you have a large population of data or a large population of things and you pick a sample out of it, especially if that sample is small compared to the large population, then for variance and standard deviation, it tends to actually be smaller than the population variance and standard deviation. It just tends to be smaller because you're picking so few things out of so many things. So they saw this. So statisticians, mathematicians, when they were coming up with all this and they were starting to work with it and use it and see how well it works, they kind of saw that it's kind of this fudginess was happening, that they could calculate the variance for the whole population, and then what they do is they take a sample, calculate the variance there, take a sample and calculate the variance there, and they just noticed that for small samples, that variance consistently underestimated, underguessed the true variance. And so this business about dividing then by 11. So they decided, well, instead of dividing by the full, we're going to divide by one less. Now there's another theoretical reason behind it, which is hard to explain. But one of the things to think about, one of the reasons just mathematically that this works, that they chose to do this. Let's say, let's say we have something like, 100 divided by 12, right? So 100 divided by 12 gives you what, 8.33 roughly, but rounded. Now let's look at 100 divided by 11. What is 100 divided by 11? So do that in your calculator real quick. What's 100 divided by 11? And 100 divided by 11 is going to be 9.090909, but roughly 9.09. So notice how dividing by a smaller number automatically makes this a little larger. And even if this wasn't 12s and 11s, I mean, if you think about this, this works for anything really. 25 divided by 5 is 5. But then if you do 25 divided by 1 less, that's automatically going to be larger because you're kind of dividing your piles. You have less piles, so each pile has to be bigger to make up the 25s. That's a good way to think of it. 25 divided by 5 is like saying you're dividing 25 into 5 piles. You got 5 in each. But if you make 4 piles out of it, those piles have to have more. So dividing by 1 less automatically makes this your result larger, basically. It makes this number larger. So like for instance, here, this is going to end up being 0.25. So it automatically kind of sizes it up. So again, remember that, so what they saw was that when you take a sample, your variance is always under the population variance, is always under guesses it. And so what they decided to do then is they just remember this. This is just a basic arithmetic calculation fact. You divide by one smaller, it automatically bumps that number up. It automatically sizes it up. So they just kind of looked at this and said, well, why don't we do that? Why don't we divide by one less? That'll automatically size, in this case, my variance up, which then should make it match the population variance a lot better. So hopefully that gives you a little bit of idea why. So that's the why, but the tag you want to make is, again, as long as we're talking about a sample instead of a population, then when you get to this variance, we're going to find the mean of our squared deviation, add all these up, but then when we divide, because it's a sample, we're going to divide by, in this case, 11, not 12, so one less. So samples, you always divide by one less for your variance. Standard deviation. Anyways, okay, so hopefully that wasn't a bunch of words and gibberish pointed at you. But that's what we need to do next. We're gonna find the variance. We're gonna find the mean of this, but because it's a sample, you add them all up, divide by 11 instead of 12. So go ahead and do that really quick. Pause on your side, I'll pause on my side. So when I add these all up, I get 394.25. Hopefully you got that when you add them up, and then we're going to divide that by 11. And what I'm getting is 35.85. So my variance here, so this is going to be my variance. So again, you don't have to write it down here. I kind of write it down here though, because again, the variance is the mean of the squared deviation. So basically my means I'm going to end up writing down here. So my variance and it is a good question of where we want to round this. So the rounding rule they're giving in the book is one more decimal place or one more place than your data. Our data is whole numbers. So we probably should round this to 35.9. Variance is about 35.9. And what this is telling me, so this is now the average squared deviation or squared distance. So all my data is on average about 35.9 square, or the squared distance is about 35.9 away from the middle. But that's squared distance. So I kind of need to undo the squared, because then if I undo the squared, I'll have the average distance. I'll have the average spread or distance that my data is away from the middle. So we need to undo the squared. And how do I undo a squared? You take a square root. So we're going to take this and then take the square root of it, and that's called, like we saw last time, that's called the standard deviation. So the standard deviation is your actual, that is the average or expected, yeah, it's just the average spread distance away from the middle that our data is. So we're going to take square root of the variance, and that is called standard deviation. So if you go and take that number you just got and then take the square root of that, let's see if I can do this on here without, but then rounded to the first decimal place, what I'm getting is 6.0. It's like 5.98, and then the decimal keeps going. So rounded to the first decimal place, that's 6.0. So this is, again, this is your standard deviation, standard distance. So my data is on average a standard, but on average about 6 away from this mean of 56.25. And if you think about that, that actually does kind of cover almost everything, right? So 56.25 minus 6 is 50.25, which covers everything except for the 49. and plus 6 is a 62, and that covers everything but the 71. But it actually kind of does cover everything well. Now we'll look at in some later sections. Actually, I think we look at it just a little bit in this section, I think later, but really in later sections, we'll look at, so how we can use the standard deviation to then describe the distribution, the shape of the data, but really describe the spread of the data to figure out, really to see how much of your data should fit 6 away from 56.25, right? So we'll get to that, but now we've got a calculation. So like I was talking about in the last video, what we want is a way to calculate and accurately describe what is our average spread of the data, not just where is the middle, but how far would we expect to see it away from the middle. And now we have it, and it's called standard deviation. Good. So that would be variance and standard deviation for this data. So based on this sample, if this sample's, if we can show that it represents an average snowy day with everybody in the town that's driving, then what we're saying is on average, you get out on a snowy day, with this handy dandy data in hand, you can expect that you'll be waiting on average about 56 minutes plus or minus 6 minutes. So maybe you get lucky and you get a 50-minute wait. Maybe you don't get lucky and you're sitting there for a little over an hour. Them's, as they say, them's the breaks. Sometimes that's just how life is. It is interesting. Again, we'll get into it in further sections, not only in this chapter, but in a chapter in the future. It is interesting that when you have large bits of not just data, but then large bits of things that happen, that life does end up being like that. It's kind of, you have a middle and you kind of expect it to be a little plus and a little minus, right? But part of the reason it's like that is actually because anytime you have large sets of data, they tend to fit the mean and the standard deviation because they tend to fit, not always, but they tend to fit what's called what we saw in an earlier section, the Bell distribution, or what's called the normal distribution. So large sets of data, measurements, things that happen, not always, but most of the time fit the Bell distribution. And because of that, we can expect things to be kind of, you can expect to hit the middle plus or minus, and that plus or minus is your standard deviation. And it's amazing how well actually that these predict events that happen. So well that, you think about, like I said, this idea of small sample out of a population, so well that they can make predictions on large populations by only taking a survey of about 2,000 people. Now that's a lot of people, but you can predict, again, within some margin of error, you can predict how things happen on large populations, million, 2 million, 30 million people, by taking a survey of about 2 to 3,000 people, and using the mean and the standard deviation from that survey. Especially in this, not in the next two sections, but in the future chapter, I'll continue to foreshadow this future chapter, but in this future chapter, we'll look at why. We'll look at kind of what justifies that why. But one of the things that I, not only right now, but also in that future chapter, I want you to just, maybe we'll get to why or what makes sense of it. But even before we get to why and what makes sense of it, and even once we see why and what makes sense of it, I don't want you to lose kind of the wonder of that. So basically, it still is going to be really weird and sort of break your mind a little that we figure the universe shouldn't work that way, that everything should have cause and effect and a reason, and this does this and this and causes this and this. But what we're basically saying here is once you have an aggregate huge population of things tend to be run by the mean and the standard deviation. And that's freaky. And hopefully once you see in a later chapter, maybe some reasons why that makes sense, it's still kind of freaky. So the universe is kind of freaky. It doesn't work. Sometimes it works the way we expect, and sometimes it doesn't work the way we expect. So Yeah, anyways, so we'll get to a little bit of that in the next couple sections whenever we get to that, and then especially in a later chapter. And you'll see kind of it works, but it's weird. It's still weird. So I don't know. Good. Variance and standard deviation. All right, let's get to another example. So calculating variance and standard deviation. So the two examples we've seen so far have been just, data sets. We saw in the last chapter, sometimes they don't give you the raw data, but they'll give you a frequency table. And we saw that, for instance, we could calculate a mean and we could figure out mode and we could figure out midpoint and all that kind of stuff using median, using a frequency table, even though we didn't have the actual data, but we used essentially the midpoints of our classes as approximations for our data, and we use that to do all our calculations, mean, median, mode, etc. So sometimes you're going to be given data like this. In fact, ideally, that's what you should have, but sometimes you're not given that. Sometimes you are given a frequency table. So the question is, could we do the same thing here? Could we do the same calculation using a frequency table? So just like the last chapter, could we get a good enough approximation from a frequency table to go ahead and still get data listed out, the deviations calculated, the squared deviations, and do this whole thing? And ends up the answer is yes. So you'll see we're gonna use the same little trick that we did in the last chapter where since we don't have the data, we know it's not gonna be exact, but we can approximate things using the midpoints of our classes. And that same trick works just as well here. So let's look at that. So let's do one line boosts. Actually, well, this should be population. This shouldn't. Let's look at this information in 19 actually. So let me erase a little bit what I have up here so we can kind of look at 19 fresh. All right, so this is pupils per teacher. So they say the following frequency distribution shows the average number of pupils per teacher in the 50 states of the United States. Find the variance and standard deviation of the data. So they're not even worried about range on this one. Variance and the standard deviation. Part of the reason we're not worried about range is we don't know the actual data. So let's talk about this for a second. So we don't know the actual data. What we do know is, so there are two states with average number of pupils somewhere between 9 and 11. 20 states, 12 to 14, 18, 15 to 17. But so for instance, this low class that we have here, we don't know exactly the values on those states. So it could be two nines, but it could be two 11s, right? And then this high, we have one state with the average class size of 24 to 26. By the way, this should be what they mean by this is K through 12 school. But we don't know if that's a 24 or 26. So our range could be as high as 26 minus a 9, or it could be as low as 24 minus 11, and we don't know. And we could use our midpoints there to get at least a close approximation. So and it may be in another book in another problem, that's actually what they would do. So you would do 25, the midpoint here, minus 10, the midpoint here, and get a range of 15. But basically it's close, but it definitely has some error there. So I think this book skips doing range just because we know there's already going to be a lot of error there. But we can do variance and standard deviation. All right. So to do variance and standard deviation, we still got to start the same. So we've got to get a table going, and we've got to list out, kind of list out our data, find a mean, and then get our deviations from the mean, and then square our deviations, etc. But like we saw last week, when you're doing this with a frequency table, we can do a bit of shortcuts in our work because we know, for instance, we have two pieces of data that are represented by this class. And since we don't know what that data is, what we're doing is we're assuming the data, we're using the midpoint of the class as our piece of data. So like here, I don't know if it's 2 9s or 2 11s, or if it's 1 9 and 1 11, it's 1 10 and 1 11. But what I can't say, what I'm going to pretend is that the midpoint of 9 and 11 is 10. So I'm going to pretend that this is 2 10s. So my first two bits of data are 2 10s. But we know the calculations we're going to be getting with that, which each of those 10s is exactly the same. So instead of doing a separate calculation for each of them, I'm going to do a calculation for one of my 10s and then just double it, because I know I got two of them. Or at least to get an approximation of this data, I'm pretending that I have 2 10s, two of the midpoints. Anyways, so I guess I'm trying to link to, hopefully that's catching, or that just brings back for you what we did last week, that we multiplied by the frequencies as a shortcut, because what we're doing here, since we don't have the actual data, is we're pretending each one of these, in this case, states fits the middle of each of these classes. It's just the midpoint. So, second here. So kind of, yeah, I feel good, but I feel like I'm getting lost in my thread. So we're gonna need, so we're gonna calculate our variance and standard deviation. Let me size this up, and also so we need to talk about a couple things with this before we start. Notice, by the way, just notice the numbers first. So for a second, stop being a math student, or just trying to do a problem in a class. So I mean, again, the data in this book comes from reliable sources. So this is all 50 states, number one. And notice there are some states with, this is K through 12, with an average number of students per teacher between 9 and 11. That is crazy. That's crazy nice. I don't know if those are states with the smallest population, so maybe that's Montana or something like that, where it's like there's not a lot of people to begin with. So, and it's pretty big geographically, so it's like it's not like you can just put everybody in a couple schools. It's, you still have to have a lot of schools everywhere. So maybe, yeah, maybe that's Montana or something like that, where it's small amount of people, large amount of space. So you're gonna have a lot of schools with a lot less people. Or maybe it's like Rhode Island or something like that, where it is a small state, but it's also a small amount of people, but it's also the, we call it the ideology, or basically behind a lot of the teaching there is to go much smaller. So if you know anything about Montessori schooling, that kind of comes from the Midwest and Northeast. But one of the philosophies of Montessori schooling is basically small class sizes, right? So, and we see that when you do education research, you see that all over the place. Small class sizes makes things better. We know that from just being in class. Small class sizes make things better. Doesn't mean you can always achieve that, right? So there's natural things that cause just class sizes to be bigger. I mean, we live in Texas, right? And everywhere, even though Texas is huge, it's got a lot of people, and basically everything, everywhere in Texas, there's a lot of people. So our class sizes are going to be bigger than other states. We just have a natural pressure of a lot of people everywhere we go. But still, we know that lower class sizes are better. So a lot of school districts, whether it's in Texas or other places, that's one of their pushes is find ways to make the class sizes smaller. So places like Montana naturally achieve it. Places like Rhode Island do it because they really are committed to that philosophy. They're committed to that philosophy of low school sizes, and they structure their schools. They structure who goes to what schools. They structure, you know, what do you call it? The way teachers are split up. They literally structure it in a way where they're trying to guarantee as much as possible a lower what do you call it? A lower student to teacher ratio. So there are some really crazy nice places to teach. And there's also some really crazy nice. So there's 20 states that somewhere between 12 and 14 average. Honestly, if you had asked me the list to guess what the average class size would be in 50 states, I would not have had the distribution be this low, honestly. Um, Now, I've only ever lived in Florida and Texas and California when I was really young, but that doesn't count. So I've only ever really lived in Florida and Texas. And so because of that, unfortunately, my whole life I've been used to class sizes more in the top end of this range, right? Um, the other thing too, this is an average from K through 12. So elementary classes tend to be smaller, high school classes tend to be bigger, but still, I would have expected most of the US to be somewhere in the 18 to 20 range. And that's not the truth. The truth is there are a lot of states. There are 20 states, 12 to 14, 18, 15 to 17. I mean, those are really nice places to teach. It is really easy. I taught high school for a year and a half, but also I've taught college for, 15 years. It is really easy to get 15 people to excellence. Um, and it's not even, it's just about it's basically literally about crowd psychology. It is 15 is small enough so you can really pay attention to everybody. You can manage everybody well. It's just easy. Literally, if you gave me classes of 15 students the rest of my life, I could get every one of them to Harvard. Um, Sort of not joking about that. But if you have a class of 25 students, at some point the population is the amount of people is big enough that it unfortunately becomes herding cats. And again, that's not saying anything about the students or even me as a teacher. That's just sociology and psychology. There's a certain number where one person cannot manage that well, right? You can't spend it, you can't pay attention as much. There are things going on that you can't manage because you just don't have attention to deal with 25 students like you do with 15 students. So that's one of the things that we're facing both in Texas and a lot of other states is that is not about bad students or a bad teacher. That's just life. That's just physical. That's reality. So what do we do about that? How do we reverse that trend? Because I guarantee you, all the good teachers I know, like when I say that, I swear to you, it's not even really an exaggeration. Every good teacher that I know can get every class of 15 students to Harvard. Period. End of story. Not 25 students. Just doesn't work. It's just physical limitations, psychology and sociology. So anyways, so there are a lot of places where it's really nice to teach and it's good to see the average this low. So that's the first thing I want to talk about is just, don't always be a student. Look at the data, especially you're in a statistics class where we have actual data for things. Look at the data, make some thoughts, do some analysis, dream. Just kind of look at what it's saying. All right. Now this is all 50 states, right? So if I was doing some analyzing about, in this case, I want variance and standard deviation for students per teacher in the US. Well, that's everything, right? That's all 50 states. So this is not a sample, this is a population. So because of that, when I go and do the variance, I'm going to be dividing by the total number of states, not the total number of states minus one. So I'm not going to do the sample thing where I subtract one. I am just going to divide by 50 when I get to variance. So that's another thing to note in your head as you go. So basically each problem you're looking at, you want to figure out, is this a sample? Is this a population? So then let's start this. We need to start this like we started these problems in the last chapter so we can find the mean, right? And that's the first thing we do need to do. So to figure out variance and standard deviation, we know that we need to find the mean. The first thing we're gonna need to do is find the midpoints of each of these classes. I won't even label the column, you kind of get the idea. I need to find the midpoint of each of these classes. So go ahead and do that really quick. It won't take you long at all. But go ahead and pause on your side. I'll pause on my side, find the midpoints of those classes. So the midpoints, again, if you're good with procedures and you kind of want to do the same procedure every time, remember you just add these two, divide by 2. But I think also if you think about a number line, you can actually see the middles of each of these. So either way, what you're going to get is the midpoint is 10 for the first class, is 13 for the second class, is 16 for the third class, it's 19 for that class, is 22 for that class, and it's 25 for that class. So the way we're going to handle our calculations is we're going to pretend that we have 2 10s, 20 13s, 18 16s, 7 19s, 2 22s, and 1 25. Now our goal again is variance and standard deviation. Deviation, distance, spread away from the middle. So the first thing is we need a middle. We need a mean. So the same way you calculated the mean in the previous chapter is what we're going to do here. So essentially we got to add them all up, but when you add them all up, you're using multiplication as a shortcut. So we got 2 10s, which means these two 10s give me a 20. You've got 20 13s. 20 times 13 ends up being 260. 60, not 2600, etc. So you're again using multiplication as a shortcut to add up all of these to get the amounts for all these. And then we're going to get the mean. We're going to add them all up and divide by 50. So you're not going to divide by the number of classes, you're going to divide by the number of states, because again, what we want is the mean number of students per state. Good. So hopefully, again, this rings bells. We did this, and we did this in the last week on the videos, and then you did it in the homework. Keep multiplying through, add them up, divide by 50, and that's going to be our mean. So go ahead and pause on your side. I'll pause on my side and see if you can get that. All right, let's see what you guys are getting. Got for this. So 13 times 20, 16 times 18. Give me a second. 180. 16. Should be 288. 288. 7 times 19. So we're just multiplying these as a shortcut so we can add everything up. 7 times 19 is 133. Times 22 is 44. We get 25 out of that. Then I'm going to add all these up, divide by 50. So again, I'm going to have my mean kind of here. This is, in some ways, this is sort of the start of building our table. So it should be easy enough. 280, 568, 6, 701, 745. 770. We're going to divide that by 50. So that's going to be, let's see, 14, 15, say 770. So that should be 15.4. So you should get 15.4 for the mean there. I'm starting, like I said, start making a table out of that. Okay. Actually, you guys kind of get the idea, but I think for this one, I'm gonna not create so many lines because I think that'll help us keep track of the calculation better. But anyways, so my mean should be about 15.4 there. Pretty darn good. That's a nice, like I said, that's a nice class size. 15, I can get everyone to Harvard. Let's see. All right. So we got our mean. So the next thing we do after the mean is we find the deviation, right? So how far is this data away from our mean? So again, what we're going to do is we're going to use our midpoint. So again, the whole point of this is just like we did on the last week when we found the mean, we use our midpoints as our proxies, as our kind of estimation. And it gets us close to whatever the real answer would have been if we had we actually, in this case, had all 50 bits of data. So each of these midpoints, I'm going to see how far they are away from 15.4. So, oh yeah, I guess let's draw some lines. So I'm going to have a column of my deviations. Yeah, so let's do that. So for each of these, you're gonna do 10 minus 15.4, 13 minus 15.4. As we go forward in this problem, again, remember though, you don't just have 110, you don't just have 113, you just want to have 116. So these frequencies are still going to come into play as we start talking about deviations and deviation, and especially our deviation squared, because you've got to account for whatever deviation you get for the 10, you got to count that you have two of those, right? And whatever deviation you get for the 13, you gotta account that you have 20 of those, etc. But for each of these, then we still need to know for that single value, what's its deviation? How far is it from the mean? So I'll go ahead and give you guys a second to do that. So pause on your side, I'll pause on my side, figure out your deviation there. All right. So the deviations of each of these midpoints, 10 minus 15.4 is negative 5.4. Sorry, 13 minus 15.4 is negative 2.4. 16 minus that is going to be 0.6. 19 minus that is going to be 3.6. 22 minus that is 6.6. 25 minus that is 9.6. So those are my deviations. So again, we can imagine now we have two bits of data that are 5.4 away from the mean, the middle. We have 20 bits of data that are 2.4 away, etc. 18 that are 0.6 away. So, all right. But we're going to go on and do the same thing. So then for each of these deviations, we then got to do deviation squared so that we can get to variance, right? So figure out your deviations, then deviation squared. So you're going to square each of these. And then we're going to find our variance, which is going to be the mean of all these deviation squareds. So first of all, really quick, go ahead and find your deviation squareds. Just pause on your side, I'll pause on my side really quick, figure out those. All right, so 5.4 squared. So let's do all the little calculations there. By the way, we know when we square a negative, so you'll notice I keep accidentally saying the positive, well, when I'm squaring them. So I'm honestly just typing 5.4 squared because you know that negative times a negative is a positive. So why waste the time typing the negative? You don't have to do that, but if that makes sense to you, that'll save you a little bit of time. Anyways, yeah, negative 5.4 squared. That is gonna give you 29.16. This first one's gonna be 29.16. Second one, negative 2.4 squared. 5.76. 5.76. Then 0.6 squared, I can tell you automatically that's 0.36. Some of these I should be able to do in my head quicker than I can type it, but let's go ahead and type it. 12.96 for this. 6.6 squared is 43.56. And 9.6 squared is 92.16. So those are my deviations. So then when we go to find the variation, I want to add up all my squared, or sorry, they're my squared deviations. I want to add up all my squared deviations and divide by and find the mean. But again, I'm not just going to add these up because this is only one of the two. So this 29.16 comes from one of these two tens, but I've got two of them. And this 5.76 comes from one of these 2013s, but I got 20 of them. So how could I size these deviations? Basically, how could I account for the fact that I actually have two of these 29.16s and 20 of these 5.6s? I have two states that give me that much deviation squared and 20 states that give me that much. How can I account for that? Good. We can use, again, multiplication as our shortcut. So again, these frequencies become our shortcut because we can just multiply by each of those. So my squared deviation, I don't have 29.16, I have 2 times 29.16 because there's two states that give me that deviation squared. And I don't have 5.76, I have this times 20. I have this times 18. This times 7, etc. So we're again going to multiply by our frequency so we can get the total deviation squared, so that I'm actually accounting for every one of the states, not just for treating each of these like there's one of them. Yeah, hopefully that, I know that makes sense, but hopefully that really connects for you. Good. So we're going to multiply these through, and then let me just figure out how I want to label this so that it's kind of consistent with the other things you guys have seen. Well, yeah, we'll just, once we have that, then we're going to have all of our squared deviations and we can add them all up. And again, because this is a population, not a sample. So this is all 50 states. This is not a sample of the states. Then when you find your mean of these deviation squareds, you're going to be dividing by 50, the population, rather than like we did on the last one, rather than like a sample. So that's what we want to do. 2 times that, 20 times that, 18 times that, etc. That'll give you all your squared deviations, add them all up, divide by 50, and that's your variance. So I'll give you guys a second to do that. All right, let's have some fun. So fun for me, I don't know. That's gonna be 58.32. That's gonna be 115.20. This is gonna be, it's gonna be 20 of them minus, so 7.2 minus 0.72. 6.48. Get that right. 2.8. Yeah, 6.48. 7 of these is gonna be what, 84, 6.3, 6.72, 17. 84, 90, 72. 2 of these is gonna be 86, actually 87.12. 2 of these is gonna be 184.32. Then I'm gonna add these all up, divide by 50, and that's gonna be my variance. And I could actually do this. Give me a second here. So 173.5 to 79. Actually, so it's 80. That's nice. 270.72. 57. 4. 530. 541. 542. 16. So these added together should give you 542.16. Stop. Should be more. Everything's pretty close to me. I guess that's why. And we'll divide that by 50. So the variance that I'm getting here is, and I guess we want to round it to one decimal place. So about 10.8. So the variance is 10.8. The squared distance, the average squared distance is 10.8, but then we're going to take a square root of that. That'll get us our standard deviation. So again, square root of variance is your standard deviation. I'm going to go ahead and take what I have in here, say 10.8432. 10.8432 square root 10.82. So when I take the square root, round to the nearest, need that. End up with about 3.3. So for all 50 states, our average class size is about 15.4, K through 12, with a standard deviation of 3.3. So the average states, so on average, the spread is going to be 15.4 plus or minus 3.3. About on average, about 3.3, maybe above or below that, what do you call it, that class size. Notice honestly that kind of makes sense. 15.4 minus 3.3 is 12.1. Gets us right about to the beginning of this class, and plus 3.3 gives us 18.7, which gets us just about to the edge of this class, maybe a little bit into this one. And that is definitely the majority of the states. And that's all, that's the 20, that's the 18, and maybe a little bit of that 7, one of them, something like that. I mean, that's it. That's definitely the majority of the states. About 39 out of the 50 states. So again, we'll look at that number later. 39 out of 50 is 68%. So 68% of our data fits mean plus or minus the standard deviation. And like I said, that is not an accident. When your samples get larger, again, we'll talk about that in a later section. 68% of your data on average fits roughly the mean plus 1 standard deviation and below 1 standard deviation. So that's actually, again, that's a nice rule of thumb that we'll learn about in the next couple sections. But surprisingly, again, when the samples are large, it's weird. It actually kind of works almost every time. It's really freaky. Anyways, good. So we can do variance and standard deviation even on a frequency table, just like we did mean on a frequency table in the last section. All right, good. So that you do need another part to this for this section. There's just a lot in this section. Every statistics books I've ever taught out of these two sections, the measures of central tendency and the measures of variation, they've just put way too much in these sections. They could easily make it 4 sections. I'd never understand why they make this 2 sections. But anyways, so there'll be a third part to this video. We'll get to that, but this will get you most of that 3.2 homework. Right, this is 3.2, yes. Okay, so start working on that 3.2 homework. I'll put these 2 videos up and the next one will be coming. See you guys next time.